Welcome to Hot Chips 32. Session 5, FPGAs and Reconfigurable Architectures.
And reconfigurable architectures. My name is Ralph Wittig. I'm a fellow at Xilinx. The first talk up is by Intel's PSG group on Agilex generation of Intel FPGAs. The speakers are Ilya Ganusov and Mahesh Iyer. Introducing the speakers, Ilya is a senior principal engineer and director of the FPGA Fabric architecture group at Intel. His research and development efforts focus on advancing FPGA core architecture and developing architectural tools and methodologies. Ilya received his PhD in electrical and computer engineering from Cornell University. Mahesh Iyer is an Intel fellow and the chief EDA architect in the PSG group at Intel. He's responsible for defining and carrying out the technical vision and direction for the Quartus compiler. Prior to working at Altera Intel, Mahesh worked at Synopsys, where he was the software architect for some of Synopsys' most successful EDA products, including Design Compiler, IC Compiler, and VCS. Mahesh received his PhD in electrical engineering from the Illinois Institute of Technology. I would like to now welcome Ilya and Mahesh to present their talk.
Agilex is Intel's first FPGA fully designed and manufactured in-house. At the heart of Agilex is the next generation FPGA core architecture built on a customized version of Intel's 10nm process node. This combination of architectural enhancements and process technology delivers over 40% higher performance or up to 40% lower power compared to our previous generation. We designed Agilex to support a wide variety of cutting-edge network and memory interfaces. It comes with multiple options for transceiver chiplets, with lane speeds up to 116 gigabits per second. Agilex is also Intel's first device supporting coherent processor attached with CXL. In terms of memory interfaces, mid-range devices support DDR4 and LPDDR4, and high-end will support DDR5, Intel Optane, and HBM2E. The Agilex architecture was tightly co-designed with the Quartus software suite through introduction of many leading-edge EDA optimizations. Agilex represents the spatial component in Intel's silicon strategy across CPU, GPU, AI, and FPGA architectures, and it's rolled out simultaneously with the introduction of Intel's One API software ecosystem. Mahesh is going to talk about Quartus EDA innovations and One API in his part of the presentation. Agilex packages use Intel's Embedded Interconnect Bridge technology, or EMIB for short, for separating transceiver silicon from the main FPGA die. We use EMIB bridges with 55 microbump pitch density for integrating different dies on a single package at a lower cost compared to using full silicon interposer. EMIB allows us to reuse the same transceiver dies between multiple generations of FPGAs. It also enables flexible pairings of the same FPGA die with different transceiver tiles to meet specific customer needs. Disaggregating transceiver silicon also allowed us to scale up the fabric die to very large capacities, while keeping programmable logic itself monolithic. This provides significant ease of use to our customers by completely eliminating the need to partition FPGA logic between multiple die slices. Now, let's look at the anatomy of a typical Agilex FPGA device and highlight a number of floorplan improvements compared to the prior generation. First, FPGA Fabric. Previous generations of FPGAs had I/O integrated as a wide column inside FPGA Fabric, which forced fabric routing to cross wide I/O columns and complicated time enclosure for many customers. In Agilex, we moved I/O columns to the periphery, which provided much more predictable time enclosure. Similar to I/O, The ARM processor complex and Secure Device Manager used to display some of the fabric sectors in Stratix 10. We moved both of these components to the corners of the device, eliminating fabric notches, which presented potential routing hotspots. As a result of these changes, Agilex device features perfectly rectangular FPGA core fabric, which simplifies customer floor planning. We also made every fabric sector identical in terms of resource composition and columns, which improves soft IP portability across the FPGA die. Each Agilex FPGA ships with a quad-core 64-bit ARM processor cluster with ECC-protected caches and multiple peripheral controllers. It also includes multi-ported front-end for coherent memory view between ARM cores and FPGA logic. In the lower left corner, we have the Secure Device Manager, containing triple redundant hard processor and accelerators to perform encryption, decryption, and authentication functions of device configuration. The SDM is responsible for multiple platform management functions, including managing configuration, responding to SEU events, and detecting tempers, as well as overseeing device boot order. Next, on the top and the bottom of each device, we have I/O banks and high-speed memory interfaces. Agilex supports all the I/O standards you would expect from a typical FPGA. These I/O banks can also be reconfigured to support standard DDR4 and DDR5 memory interfaces. High-end devices also support Intel's Optane persistent memory with capacities up to 8 TB per FPGA, which is ideal for server memory expansion and acceleration with CXL. Select high-end devices also support HBM2E. Finally, disaggregated transceiver tiles attached to the fabric die via EMU bridges on the right and left sides of the device. The Agilex family comes with 5 types of tiles with a wide range of lane speeds and supporting different protocols including Ethernet, PCIe, CXL, and dozens of other serial interfaces. The Agilex fabric die is implemented on Intel's 10nm process node. As this universal curve shows, 10nm process delivered significant improvements in both performance and power efficiency over Intel's 14nm node, which we use for Stratix 10. However, we got more out of 10nm by adding extensive customizations addressing specific FPGA needs. First, we optimized the metal stack by adjusting number of metal layers and metal track width, spacing, and aspect ratio. We also used wider poly pitch for core fabric transistors to get better performance, and tuned transistor thresholds to improve performance per watt. Modern FPGAs are used in increasingly power-constrained environments. So next, we lowered nominal voltage by about 100 mV to get better power efficiency. As a result, we relied on architectural innovation to achieve our 40% performance improvement target while operating at a lower voltage. Now, let's look at some of the core architectural innovations in programmable logic. Similar to Stratix 10, each fabric sector consists of columns of programmable logic and distributed memory, shown here in blue, 20 kilobit memory banks, shown in green, and DSP blocks, shown in purple. In Agilex, we improved programmable logic speed by 50% and extended DSP capabilities to address computational requirements of emerging AI workloads. In particular, we doubled per DSP throughput for bfloat16, FP19, FP16, and int8 formats. In terms of clocking resources, we maintained configurable H3 clocking architecture introduced in Stratix 10 and enhanced it with embedded programmable clock delays. The Quartus compiler uses clock delays to introduce intentional skew on critical paths to achieve high performance. Programmable hyperflex routing ties all these blocks together. Routing is not mentioned on the datasheets, but it is the single biggest contributor to FPGA fabric performance, power, and area, and it went through the biggest transformation in Agilex. Let's look at an example of a typical programmable routing segment, which crosses 4 architecture columns in Stratix 10 and prior FPGAs. Each routing stage starts with a wide MUX, followed by a buffer, which drives a wire transporting data signal across 4 fabric columns. Routing segments also fan out to other routing MUXes as they cross architectural columns on the way. This high fan-in, High fan-out architecture worked well for many generations of Stratix FPGAs, but it did not scale well to 10 nanometer. So we completely re-architected routing in Agilex and replaced wide, high fan-out muxes with narrow and much faster muxes fanning out at a single destination column or row. We also carefully redesigned routing pattern and adjusted number of routing muxes to maintain and improve routability relative to our baseline Stratix 10 architecture. This diagram compares absolute delay for crossing 4 architecture columns in Stratix 10 in orange and Agilex in blue. You can see that in Stratix 10, traveling across 4 columns takes between 150 to 250 picoseconds, and in Agilex, most of the equivalent paths are below 100, providing more than 2x improvement in delay on average. Global routing does not talk to programmable logic directly. Sparse crossbar between routing and ALMs funnels hundreds of global routing tracks into few logic input pins. In Stratix 10 and prior generations, the internal structure of the crossbar was represented by long routing tracks fanning out to wide muxes. In Agilex, we repartitioned this crossbar into faster lanes with reduced logic span, while retaining some of the long lanes but reducing their fan-out. This also allowed us to switch to narrower, faster muxes, similar to what we did in global routing. On this chart, you can see a relative comparison of every single path through the sparse crossbar in Stratix 10 and Agilex. In Stratix 10, going through this crossbar takes between 130 and 200 picoseconds. And in Agilex, we contained this delay to range between 55 and 65 picoseconds, providing 2.5 times faster propagation delay on average. In addition to that, Quartus enhanced its placement algorithms to align logic placement to these faster crossbar lanes. Now, let's look at how all these improvements in fabric floorplan, process technology, and microarchitecture roll up at the application level. Here we compare performance on a set of 65 benchmark designs across a wide range of applications, compiled from the same source code without any modifications. Agilex achieved more than 40% high performance on average. And the speedup is broad-based. Every design runs faster, with performance uplift ranging from 20% to almost 100% on some designs. So we see consistent speedup across many application domains, including wired and wireless communications, video processing, ADAS, AI, and many others. Overall, Agilex is on track to deliver the highest single-generation performance uplift since the introduction of original Stratix line of FPGAs almost 20 years ago. Next, let's talk about off-chip connectivity options provided in Agilex FPGAs. Agilex fabric dies can be paired with a choice of 5 transceiver chiplets supporting different standards and serial link speeds. 3 of those tiles shown on the right, P-tile, H-tile, and E-tile, are available both in Stratix 10 and Agilex FPGAs. The 2 tiles on the left, R-tile and F-tile, were designed specifically for Agilex. So let's talk about these tiles in more detail. R-tile is focused on delivering PCIe Gen 5 connectivity and enabling coherent CPU attached with CXL. Each tile contains 16 lanes of 32 gig NRZ SerDes, which can be configured to bypass all the hard IP controls on the tile to talk directly to FPGA fabric. PCIe lanes are buffer capable into by 16, by 8, and by 4 modes, and CXL can be configured into 1 by 16 or 1 by 8 modes. Both PCIe and CXL come with a typical number of supported physical and virtual functions, which can be extended thanks to the configurable bypass for customized register topologies. CXL support in R-tile makes Agilex FPGAs Intel's first CXL-attached device with full support for Type 1, Type 2, and Type 3 configurations defined in CXL spec. Hardened IP on this transceiver tile provides a good balance between efficiency of hardened controller logic and flexibility of FPGA fabric. It opens exciting new opportunities in heterogeneous CPU FPGA acceleration. Now let's talk about F-tile. F-tile is focused on high-speed networking. Each tile contains 2 groups of transceiver PHYs. The first group has 4 lanes of the highest speed 116 gig SerDes. The second group can be configured as either 12 lanes of 58 gig PAM4 or 16 lanes of 32 gig NRZ. As I mentioned before, FTILE is focused on providing advanced networking capabilities with hardened IP for MAC, PCS, and forward error correction. Transceiver lanes are bifurcatable into multiple configurations, ranging from 10 to 400 gigabit Ethernet, and FTILE supports 600 gigabit interlocking or flex Ethernet. As it is typical for a solid FPGA platform, it also supports an alphabet soup of other protocols, and PCIe Gen 4 with precise time management. The real star of the FTILE is the highest speed 116 gig transceiver. In 2019, Intel was the first company to publicly demonstrate fully operational 116 gig long reach SerDes. It is built on a different flavor of Intel's 10nm process, and we demonstrated spec compliance across 106, 112, and 116 gig data rates. We showed robust operation at high insertion loss and delivering ultra-low bit error rate 2 orders of magnitude better than the specification. The fact that we can support up to 116 gig data rates adds design margin for our customers and enables extension to emerging standards. 116 gig transmitter is based on DAC architecture with more than 5 feed-forward equalization taps. It also uses quarter-rate clocking to achieve lower power. RX is designed using advanced ADC-based architecture, which enables signal processing and correction in the digital domain. This also positions this transceiver architecture for scaling up to high speeds and to future process nodes. Now let's look at how all these features and capabilities combine our product family plan. The Agilex device family plan starts with the F series, which is targeted at the widest range of applications. It features fabric dies with logic capacities up to 2.7 million logic elements, up to 35 megabytes of on-chip memory, and up to 8,500 DSP blocks. It also supports serial links with speeds up to 58 gigabits per second per lane, Gen 4 PCIe, and DDR4 memory interfaces. The I series is targeted at a higher performance and higher bandwidth applications with support for coherent CPU attach. The I series uses bigger fabric dies from the F series and pushes transceiver bandwidth to 116 gig and upgrades PCIe to Gen 5. The M series is the highest end of the family. It pushes fabric die to larger capacities and upgrades off-chip memory interfaces from DDR4 to DDR5 and adds supports for Intel's Optane. All devices in Agilex family come with Secure Device Manager and a quad-core ARM complex. The I series and M series support coherent attached to Xeon with CXL, and the highest-end M series devices come with support for HBM2E. Now I'll pass on to Mahesh to talk about software EDA innovations and One API ecosystem.
Thank you, Ilya. I will now describe some of the key features in our Quartus software that enabled all the performance improvements in Agilex. Agilex features a next-generation version of our HyperFlex architecture that was first introduced in our Stratix 10 product. The architecture features programmable registers everywhere in the core FPGA fabric, on the interconnect routing segments, and on the inputs of logic blocks. Agilex also features an ASIC-style clocking architecture. Our Quartus Prime Pro software has been co-designed with this new FPGA architecture, building in fine-grained retiming and retiming awareness throughout the flow, including late-stage retiming and clock skew optimizations with accurate delays. The traditional FPGA design implementation flow starts with logic synthesis, followed by periphery placement and clock allocation. Next, the logic elements are placed and clustered to the ALMs and labs on the FPGA. Lastly, all the connections in the user's design are routed using the programmable routing fabric of the FPGA. Physical synthesis is mostly done in the pre-route stages of the flow to surgically fix critical paths as they appear in the various parts of the flow. With our HyperFlex architecture in Agilex, the Quartus compiler flow has been significantly revamped to be highly retiming-centric. Quartus now allows for late-stage global retiming and clock skew optimization with accurate delays very easily without the need to reroute any connections. We also introduce a new incremental post-route physical synthesis step that unlocks additional fmax. The earlier parts of the flow, like synthesis, placement, and routing, were also made retiming aware so that they can fix the critical paths that cannot be fixed by retiming. Lastly, our clock allocation step is also guided by placement locations of the flip-flops and performs design-specific clock routing. Let's understand some of the details of logic retiming. Logic retiming is a sequential optimization technique to improve performance. The objectives are to maximize performance with the minimum number of registers used for this purpose. Retiming modifies a netlist structurally, as shown in the pictures here, through forward and backward retiming moves across the combinational and interconnect elements. A graph-based formulation for global retiming models the combinational elements as vertices in the graph, and the edges represent connections between those nodes, with weights representing the number of registers on that edge. An R variable is associated with each node to indicate how many registers need to move across that node in the process of retiming. A simple equation on each edge constrains a new weight using the old weight and the R variables of the nodes. The R variables are then globally solved with these constraints along with the timing constraints to achieve the optimal performance. Let's now understand some of the sequential equivalence aspects of retiming. In this simple example circuit, let's assume we forward retime the flip-flop F1 to its fan-out branches as shown. This seems like a pretty benign retiming move. However, these two circuits are not functionally equivalent. Let's understand why so. A single vector A equal to 0, B equal to 1 resets the original circuit independent of its initial states and produces H equal to 0. However, in the retime circuit, for the initial state F1A equal to 0, F1B equal to 1, and F2 equal to 1, the same vector produces H equal to 1. This means these two circuits are not equal as determined by a sequential formal verifier. So how did we solve this problem? We created two solutions. The first one introduced programmable initial states in the hardware, which cost area. The retimer computes the initial states as it moves the registers in compliance with the functionality of the combinational nodes. However, in some cases, the retimer will get stuck when it encounters conflicting initial states as shown in the fan-out branch example here. The second solution introduces the notion of C-cycle retiming in software. Here, a retime circuit is shown to be a C-cycle delayed replacement of the original circuit, where C is pessimistically computed by the retimer. The reset sequence of the retime circuit is computed by prepending C empty clock cycles to the reset sequence of the original circuit. In the circuits I showed earlier, the two circuits actually become equal with C equal to 1. Now there's also a third mode, which is the hybrid between these two, where the user-specified initial states are respected by the software and all other flip-flops are treated as don't care, enabling C-cycle retiming for them. With all these technologies, we achieved a dramatic improvement in fmax, 25% average increase in fmax from the retiming-related optimizations and 8% average increase in fmax from the physical synthesis optimizations. Now let's switch gears and understand the verification aspects of retiming. Retiming has had very limited success in the ASIC EDA world for over 3 decades because of the lack of scalable sequential verification tools. We solved this verification problem using a breakthrough technique called rewind verification. Since retiming operations are reversible, we create a mathematical formulation to attempt to retime the retime circuit back to the original circuit. Solving this formulation successfully indicates that the retimer modified the circuit correctly. A failure, on the other hand, indicates a bug in the retimer. Of course, there could always be a bug in the solver, but we assume the solver is bug-free. And in this case, the solver produces precise debugging information. We separately verify the initial states as well as perform C-cycle verification that is beyond the capability of any commercial formal verifier today. Our technique runs 3 orders of magnitude faster than a commercial formal verifier. Now let's understand the relationship between clock skew optimization, time borrowing, and retiming. In this example circuit, through fine-grained retiming across the combinational elements and interconnect wires, we can achieve a clock period of 3 nanoseconds. The best achievable clock period, on the other hand, with clock skew or time borrowing is 3.2 nanosecond. Although this example shows that retiming does better than clock skew and time borrowing, in general, the relationship between retiming, clock skew optimization, and time borrowing is shown in the picture here. Each of these optimizations have their own unique strengths. In Agilex, we have introduced a flexible clock skewing capabilities in the hardware. Quartus then leverages this capability to further optimize the performance by an average 4% that is complementary to the performance gains from retiming. Let's also now understand all the different design entry options into the FPGA. In addition to the traditional design entry, we offer several higher-level design entry options to target a broad spectrum of FPGA users. You can think of developers split into two sets: direct programming users who write code in MATLAB, C, C++, or OpenCL, which compiles directly to the FPGA. Our high-level design tools support all these different front ends in Agilex. On the other side, we enable API programmers to utilize the FPGA via a rich set of pre-written and pre-optimized libraries or overlays. Our One API offering is a compiler and toolchain that is built around Intel Data Parallel C++ language, presenting a unified programming model for direct programming as well as API programming across all of Intel Silicon, including scalar, vector, matrix, and spatial architectures. This tool is layered on top of our existing OpenCL offering, which has Quartus Prime Pro as its foundation software. Our vision is to provide pre-optimized libraries of APIs and frameworks, analysis and debug tools, and vTune-based profilers that are portable across all of Intel Silicon. With that, I will end our talk here. Thank you.
Thank you, Ilya and Mahesh. Great talk. Really appreciate it. We have time for a few questions. I see the Slack channels have been quite active already. Ilya, thank you for jumping in and answering some of the questions. I would like to pull out a few more to get a live response on in this Q&A session here. Perhaps the first question actually came in from Patrick. He was actually wondering what the process technologies are that you're using in your main die and also in the chiplets. In question, in particular, is the Agilex manufactured in 10 nanometers or in 10 nanometer superfin or 10 nanometer enhanced superfin? So which processes are you using for which chiplets?
The fabric die is manufactured on a 10 nanometer superfin. And as I described, there are many enhancements which we've done specific for FPGA, in particular, a lot of optimizations in the metal stack. And we continuously, try to improve the process, and subsequent devices in the family may leverage some of the enhancements in the transistor technology as well.
Okay, thank you, Ilya. A question from Manoj Roge. He would like to know if you can answer or comment about the latency, round-trip latency, TX to RX through EMIB on the R-tile, the 32 gigabit SerDes. If you happen to know.
So this is specifically about the R-tile? That's the question?
The R-tile round-trip latency, bypassing PCS and MAC.
Okay. I don't have a question on top of my head, so I'll get back to Manoj on this after talking to our tile architects.
Okay, thank you. Hamid Reza Zuhuri would like to know if there's any plans to bring out new HARP machines combining Xeon CPUs with Agilex FPGAs in the same package.
We don't have anything to regularly disclose at the moment, but it will be great if Hamid follows up with us offline.
So I have a related question. That is, you're using EMIB technology quite nicely for all the different SerDes tiles. Can you foresee a use of other packaging technologies from Intel, particularly for Veros, for any use in FPGAs?
Right. So we use EMIB for tiles, and we use it for HBM. And there's some other experimental projects we announced with other companies to create a chiplet ecosystem. And as you mentioned, Intel has many different packaging technologies, so we have continuously working on looking at different opportunities, how to combine different chiplets with FPGA using this advanced packaging technologies, but we don't have anything to disclose at the moment.
Okay, thank you, Ilya. Some questions on the actual FPGA fabric. Question by Bob Siller. He would like to know if Agilex features anything like an embedded network on chip to connect together the hard IP blocks to reduce routing congestion.
Right. So we enhanced FPGA routing significantly, and as I mentioned in the talk, we actually improved routability compared to Stratix 10 generation FPGAs. So the combination of the new routing architecture and HyperFlex registers make it very flexible, and we mainly rely on soft knock capabilities to route wide buses within the fabric.
Thank you, Ilya. A related question by Alireza Kaviani. Are there any major changes to the register everywhere interconnect strategy of Stratix 10 in the new Agilex? Will we have flops in all interconnects in Agilex?
Right. So we made big changes to HyperFlex and Agilex while retaining most of their performance capabilities. We optimized the number of HyperFlex registers significantly by reducing their overall count by more than 2x, while remaining all their Fmax retiming capabilities that Mahesh talked about. So overall, we have enough to exploit into 100%. So that's kind of the big change that we've done.
The other aspect is that we also optimized it simultaneously for setup and hold characteristics. And we also matured the algorithms in Quartus significantly to support HyperFlex.
Thank you, Mahesh. We have another question by Hamid Reza Zahuri. Big versions of Stratix 10 used 100 gigabyte plus of memory for one place and route instance. Can you comment on the memory footprint requirements for place and route of Agilex devices?
The memory footprint required for Quartus, that's the question, right?
That's correct, yes.
We are, our intent is to keep it under 64 gigabytes of memory. That's a short answer.
Great answer. Thank you. Thank you, Mahesh. So I would like to thank Mahesh and Ilya one more time. Really appreciate their time this morning for the great presentation and also for very interactive live Q&A. They are on Slack and continuing to answer questions. Really appreciate that. Thank you both. I'd like to introduce the next talk in our session this morning. This next talk is by Xilinx on the Versal Premium series. We have three presenters in this talk, Martin Voogel, Yohan, Frans, and Matt Ouellette. Martin Voogel is a distinguished engineer in Xilinx's Silicon Architecture Group. He's currently focused on topics including future device family definitions, top-level architecture, block architecture, SerDes, I/O, clocking, CLE, power. Before he joined Xilinx in his current position, he worked for several years at Tabula, a silicon startup company, where he was a lead IC design engineer. Martin holds an MSEE degree from Twente University in the Netherlands. Johan Frans is leading the development of the transceivers and wired communication IPs at Xilinx. Prior to joining Xilinx, Johan was with Rambus, where he worked on high-performance serial links and memory interfaces. Johan holds a bachelor degree from Bandung Institute of Technology in Indonesia and a master's degree in electrical engineering from Stanford University. Matt Ouellette is a director in Xilinx's product planning team. He's focused on silicon definition, in particular on accelerators and AI technologies. Matt spent many years as a developer on a range of different FPGA-based systems, RF signal processing, automotive infotainment, and NIC applications. Matt holds a bachelor's degree from the University of Maryland at College Park. Martin, Johan, and Matt, please go ahead with your presentation.
I'm Martin Voogel. I'm in Xilinx's Silicon Architecture team, and I'm one of 3 presenters today speaking to you about Xilinx's Versal Premium device family. I will start with an overview of the Versal family and then focus on the Premium subfamily. Next, we will take a look at key blocks and features in Premium and how they all work together. We will then discuss aspects of the Premium device architecture. And finally, we will take a look at a few key use cases that take advantage of the Premium features. Versal ACAP is a platform that is adaptable at every level, making applications future-proof to changing compute and communication protocol standards. 3 engines enable this in different ways, just like today's CPUs, GPUs, and FPGAs, but all on one single heterogeneous architecture. First, scalar engines, the ARM A72 and R5 cores. Adaptable engines, the programmable logic, and intelligent engines are DSPs. The platform has a software programmable infrastructure. Pre-engineered connectivity of critical compute interfaces like PCIe and DDR are available at boot without the need for place on route or timing closure. Software programmable NOC ties all the engine's peripherals and dedicated blocks together. Versal was designed on TSMC 7nm FinFET process. Versal Premium has integration of networked, power-optimized cores for bandwidth, security, and compute. PCIe Gen 5 with cache coherency and built-in DMA for the high-performance connectivity to host processors. 112 gigabit per second PAM4 transceivers, robust Ethernet and interlocking cores for network connectivity, and built-in crypto engines for high-speed security. These cores provide pre-engineered infrastructure for networks and clouds. Versal provides streamlined connectivity to data center compute infrastructure. The hardened shell is off-the-shelf connectivity for compute. NOC, DDR, PCIe 5, processor, transceivers, and Ethernet. Communication to CPU host and system memory are available as soon as ACAP is turned on. This is different from traditional FPGAs where configuration is slower and more complex. The role is the application or kernels that are running on the accelerator. NOC enables the rapid swapping of kernels for virtualized accelerators. In traditional FPGAs, logic resources for shell functionality would take up a large portion of the device, none of which provide application acceleration or differentiating value. A high-bandwidth programmable NOC connects engines and hard IP together. Unlike typical NOC in an ASSP or ASIC, it can be programmed for different data flows between high-speed IOs and engines and has the ability to prioritize between throughput, latency, and bit widths. Kernels on programmable logic have easy NOC entry and exit points. We can move data from IO to fabric without complex floor planning. NOC brings hardened connectivity to Versal's integrated memory controllers and PCIe without PNR, enabling communication with external DDR and CPU at boot. It has a software programmable interface to the platform. One of the highlights of the Premium family in Versal is hardened integration of networked IP engines together with 112 gigabit per second PAM4 SerDes. In prior products, implementing these IP would take up large amounts of programmable logic resources. To match Premium's networked IP capability in 16nm products, an additional 22 FPGAs would be needed. These hardened IP free up programmable logic resources for customer functions that differentiate their products. Let's talk about key blocks and features. Premium uses its building blocks in an adaptable manner to build differentiated silicon products. Let's start with a traditional FPGA. We add to that a hardened NOC and processor backbone that is present in every Versal device. Versal device floor plans include 3 types of dedicated memory slots for memory controllers, protocol engines, and SerDes respectively. Populate the bottom row of this chip with DDR4 memory controllers. We may put them on top also, and we may put different controllers in the future. The memory controllers and the hardened NOC together form the configurable memory subsystem. We then populate multiple columns in the programmable logic with various protocol engines: CPM, PCIe 5, Ethernet engines, high-speed crypto, and interlocking. We populate columns on the left and right chip edges with a combination of 28 gigabit per second GTY and 112 gigabit per second GTM. The engines and the SerDes together with programmable logic form adaptable high-speed interfaces with software programmability within blocks and between blocks. These flexible interfaces may span across SLR boundaries. Now, within this hardware, a user design can swap in and out kernels at runtime which are adaptable. The resulting architecture is an adaptable SoC with enormous bandwidth and compute.
Hi, I am Yohan Frans. I'm with Xilinx Wired Communications Engineering Team. Here's an example on how to build 1.2 terabit per second SmartPHY in Versal Premium. On the left, we have 12 ports of existing 100 gig optics, and on the right, 3 ports of emerging 400 gig optics. We take in traffic from the left, do some kind of processing at speed, then send it to the right and vice versa on the other direction. The SerDes and hardened Macs provide the required protocol connectivity, so users don't need to worry about that. Instead, they can focus their effort on building adaptable custom logic for the emerging standards. 400 gigabit per second hardened crypto core is used to implement security protocols like MACsec or IPsec. Custom at-suite processing is implemented in the programmable logic. And if deeper processing is needed, the NOC and memory controller provide high bandwidth access to external memory. For systems with higher number of client-side ports at lower rate, the additional ports can be added without consuming programmable logic resources. Lastly, future networking protocols like 800 gigabit Ethernet, they're currently not fully supported by the hardened protocol engines, can be implemented in the programmable logic, while taking advantage of some hardened subfunction that do exist in the protocol engines. In this case, a FEC subfunction, for example. On the following slides, I'll go over each one of the protocol engines and SerDes blocks in more details. Let's start with DCMAC. DCMAC gives us up to 600 gig of Ethernet bandwidth. It can be configured in various rates, 1 by 400, 3 by 200, 6 by 100. It is channelized on the Mac side, supports up to 40 channels, and each channel doesn't have to be tied to a particular Ethernet rate. DCMAC handles all protocol-related functions, MAC, PCS, FAC, including handshaking, synchronization, and error checking. It has the ability to report all types of network statistics, total bytes or packets received, good packets, bad packets, packet size histogram, and more. An important feature to highlight here is that each subblock, MAC, PCS, FAC, has its own dedicated input-output interface to the programmable logic. This is important for 2 reasons. First, user can insert custom logic between 2 subblocks. In this case, I'm showing FlexeShim custom logic or next-gen OTN custom logic that can be inserted between Mac and PCS subblocks. Secondly, user can use the subblocks independently. For example, the FAC subblock can be used for OTN, while at the same time, the Mac subblock is being used for a completely different application. Mirroring DCMAC, MRMAC performs similar functions with similar configurability at 100 gigabit per second peak rate down to 10 gig PCS granularity. We provide a hardened 600 gig Etherlock block, mostly used for chip-to-chip application, with FAC support, channelized interfaces, and built-in flow control. The interlock block supports up to 24 lanes, which enables multiple sessions and applications to interact at the same time. One of today's challenges is to be able to secure network traffic without impacting performance. Traditionally, the option was to offload the encryption engine for offline processing with major latency implication. In contrast, the 400 gig hardened crypto engine, HSC, performs encryption at line rate. The fact that it's line rate is critical. Basically, it's a bump in the wire. The HSC provides up to 400 gig of bulk crypto capability of up to 40 channels. It consists of 3 blocks: AES GCM encryption block, decryption block, and management block that deals with control, statistics, key table, and known answer test. Security protocols such as MACsec and IPsec are provided as soft IP in the programmable logic around the hardened HSC core. As an example, the provided MaxTech solution here is implemented in program logic that includes FIFOs, header processing, SA lookup, and flow control. At the edge of the die, SerDes blocks provide high-speed raw transport in and out the chip. In Versal Premium, we use two flavors of SerDes, GTYP, shown in dark gray, and GTM, shown in light gray. Why do we need two flavors of SerDes? Long-reach PAM4 performance is very sensitive to residual ISI, so it generally requires ADC DSP architecture for robustness. Because of this, the area is larger than conventional SerDes, so we do still need smaller SerDes, of course, for lower end product and area efficiency in general. On top of that, many protocols such as PCI SRIS for storage and SATA and DisplayPort require very high bandwidth clock recovery to track spread spectrum clocking. Supporting this in ADC-based SerDes will of course give our users even more flexibility, but technically this is still very challenging. We are currently working on this for a future product. In ADC-based receiver, the signal goes through analog equalizer stages, gets digitized, and further digitally equalized in the DSP block. In 7nm FinFET, we learned that the process is really geared towards minimum size CMOS gates. So based on that, we decided to build receiver data and clock path using CMOS gates. Even analog blocks such as equalizers, amplifiers, and phase interpolators are built using minimum-sized CMOS inverters as building blocks. GTM's configurable ADC and DSP is needed to support many use cases with optimum power and performance. The use cases include long-reach PAM4, chip-to-optical module, legacy lower rates NRZ, and XSR die-to-die interface. Supporting XSR die-to-die interface is not trivial. The two dies can come from different foundries, so the standard really allows the transmitter common mode to have a very wide range. Since there's really no space to put AC coupling capacitor on package for level shifting, the receiver has to handle all this wide range of common mode. This is not an easy task at 112 gig PAM4. We built test silicons to prove our SerDes before putting them in a product. As shown here, it is able to achieve better than 1E-8 prefect BER over 37.5 dB channel loss. This slide shows the summary of our protocol engines and SerDes blocks.
Versal Premium provides two types of PCIe blocks. The first is integrated into CPM5 in the SoC shell. PCIe and C6 features include integrated QDMA, integrated coherent C6 subsystem with 4.3 terabits per second coherent mesh interconnect, 1 terabit per second coherent accelerator attached memory, 800 gigabit per second coherent ports for accelerators, and C6 request, home, and slave agents in any combination. This block is available at boot with dedicated connectivity over NOC to DDR. The second type of PCIe block supported are hardened PCIe CXL controllers distributed in the programmable logic. CXL is implemented with a combination of this hard IP and the programmable logic. Premium provides SoCs with up to 8 controllers, which can drive up to 8 NVMe endpoints with an aggregate bandwidth of 256 gigabytes per second. This block is Fabric's connection to the outside world over PCIe or C6. Since Versal devices have different widths and heights, NOC topology and hardware can vary with different floor plans. Depending on what IP exists in device and its use, we can choose to have fewer or more NOC resources. The same NOC building blocks are used in a modular manner to build different topologies. A NOC channel has 8 virtual channels. A row has over a terabits per second bidirectional bandwidth for 4 channels. A column has half of that. Data with QoS, address mapping, and routes are made software programmable. NOC transport uses the NOC packet protocol. It maps to and from AXI memory mapped and stream with end-to-end ECC protection. The NOC consists of 3 components: the NMU, the NSU, which are on and off ramps, and the switch, which has a routing table and defines which NMU talks to which NSU. Rows and columns have multiple physical channels. 8 virtual channels provide independent non-blocking data flows, and traffic is packetized. This AI engine use case example demonstrates various data flows over the NOC. AI engines are present in non-premium devices. Blue data represents a PCIe host reading and writing from and to DDR or programmable logic, and processor reading and writing from and to DDR and controlling programmable logic and AI engine. The red data represents programmable logic accessing DDR and AI engine, and the green data represents AI engine accessing DDR and programmable logic. Various sources and destinations are shown. NOC provides high-speed interconnect, no programmable logic resources are consumed. The NOC compiler is fast. The result is that easier design in programmable logic. NOC is scalable. Different Versal devices have different NOC resource requirements. Wider devices have more memory controllers or accelerators at top and bottom. The number of VNOC scales accordingly. One VNOC can carry the bandwidth of one 64-bit DDR channel. Taller devices have more programmable logic. Each fabric row has one VNOC on and off ramp. The number of ramps in fabric scales with device height. Taller devices in stacked silicon integration have VNOC extended with die-to-die connections. Versal's memory subsystem has configurable bandwidth and QoS allocation. It has 4 ports with read and write virtual channels. Traffic is not spread equally across 4 ports. They have programmable QoS settings. Controls enable, for example, real-time guarantees or throughput guarantees. It has a 256-bit wide DDR that can be configured as 4 by 64 bits or 8 by 32. DDR supports up to 3.2 gigabit per second and LPDDR4 up to 4.2 gig. The memory subsystem complements incredible amounts of on-chip RAM and is used for off-chip buffering at DRAM capacities. Premium supports 702 high-performance XPIO for DDR, MIPI, and other I/O standards, and up to 122 high-density multi-protocol I/O for up to 3.3 volt standards. In ACAP devices, programmable logic is surrounded by a hard SoC shell which is up and running at boot. Stacked silicon interposer technology combines multiple SLRs. NOC has pre-engineered timing of critical paths. This eases kernel placement and easy swapping at NOC ports. Thanks to regularity of programmable logic fabric patterns within a device, kernels may be relocated between identical regions, possibly without recompile, since timing and bitstream segments are identical. Thanks to regularity of fabric patterns between devices, kernels may be relocated between devices when migrating a design to a different device. Premium uses 4th generation SSIT technology, which utilizes TSMC's CoWoS process. SLRs are assembled on a passive interposer that utilizes TSVs to connect C4 bumps straight to SLRs. SSIT enables large logic capacity with devices up to 2x reticle limit. Reticle size constraints come from fab litho steppers and has not changed. Super interposers require 2 exposures and wire stitching at exposure overlaps. SSIT reduces the number of tapeouts required for a diverse product portfolio, and Premium utilizes heterogeneous SLR use. SSIT has favorable economics. SLRs have been tested to be good before assembled on the interposer. Cost scales linearly with device size versus exponentially for monolithic devices. Thanks to TSVs, even in beachfront areas, which are covered by chip-to-chip wires and microbumps, power can go straight up from C4 to SLR. SSIT connectivity delivers programmable logic to chip-to-chip connections of 15 terabits per second over 20,000 wires. NOC chip-to-chip connections over 2 terabits per second over 4 VNOCs, and 120 global clocks cross the boundaries. SerDes interfaces extend across boundaries to enable flexible placement. 3 GTM quad blocks are needed for a 600 gig interface. Ref clocks are crossing for channel bonding. Previously unused interposer tracks on SLR interiors are now used to provide an additional 5 terabits per second horizontal bandwidth and 3 terabits per second vertical. Premium added several SSIT connectivity improvements. Inter-SLR super long lines are distributed instead of concentrated. This increases the number of channels, which reduces horizontal track demand. Horizontal congestion is reduced by half, routability is 5% better, and we see a 40% reduction in horizontal wire length. Previously unused interposer tracks on SLR interiors are now used to add intra-SLR connections. Long wires on interposers are 30% faster. This reduces routing congestion. We see 8% horizontal wire length reduction and 6% vertical. We added VNOC to VNOC inter-SLR connections to scale the NOC with taller devices.
Hi there, my name is Matt Ouellette. I work in the Silicon Product Planning team here at Xilinx, and I'm here today to tell you all about the use cases Versal Premium will unlock in the marketplace. Due in large part to the slowdown in Moore's Law, Xilinx has been focusing more than ever on architecture. The advancements in Versal allow us to deliver over 2x our previous generation, beyond the process node alone. As you can see here in the figure of merit comparison to our previous generation Vertex UltraScale Plus VU13P device, Versal Premium delivers over 2x in system protocol bandwidth, over 2x in int8 compute, over 3x in available logic capacity, as well as significant increases in on-chip memory and floating point compute. These increases stem from the many Versal architectural advancements. It's an achievement we're incredibly proud of and excited to share with you today. Let's look at some of the use cases Versal Premium will unlock in the market. The target markets for Versal Premium spans wired communications, data center, test and measurement, and aerospace and defense. One of the lead use cases for Versal Premium is enabling next-generation data center interconnect equipment. As data centers move to 400 gig and eventually 800 gig, the infrastructure will need flexibility. Whether it is facilitating FEC translation to long-haul modems, keeping switches fully utilized by translating SerDes rates, or supporting the evolution of coherent optics, we can facilitate a wide range of DCI bridging use cases in Versal Premium. The future is never backwards compatible, and we fill that gap for our customers. Many AI HPC applications face processing, memory, and data movement bottlenecks that can be addressed by the combination of terabit per second I/O and high amounts of flexible custom logic available in Versal Premium. In these use cases, supplemental inline processing is helpful to achieve best performance from the compute ASIC. Shown here is one such system, a Versal device connected to a compute ASIC via high-speed SerDes performing inline processing at hardware rates. Examples of such functions are building real-time histograms or data compression. To help with scaling compute nodes, flexible high-speed network interfaces are available to connect to other ASICs via scale-out protocols. With the integration of custom logic, tightly coupled and high bandwidth on-chip memory, and high-speed SerDes, Versal Premium can help unlock many of these use cases in the market. Xilinx has a long history working with test equipment vendors, and one that we value quite a bit, as these companies inherently operate at the bleeding edge of protocol adoption. Shown here is one example system, an 800 gig L2, L3 network tester designed to test cloud and data center interconnect equipment. The adaptable hardware and integrated high-speed I/O make Versal Premium devices well suited to handle these test applications, both on the high-speed I/O side as well as the compute side, handling custom analytics and processing of all the collected test data. We're really excited to launch Versal Premium out into the marketplace to unlock this wide range of applications.
Versal Premium is fabricated in TSMC's 7nm FinFET technology. Interposers are built with TSMC's chip-on-wafer-on-substrate technology. Premium has up to 92 billion transistors in a single device. Maximum performance in Premium is over 100 TOPS int8 in Fabric, close to 100 TOPS int8 in DSP, 23 teraflops FP32 in DSP, over 100 terabytes per second reg file bandwidth, over 100 terabytes per second on-chip memory, almost 10 terabits per second SerDes, and over 100 gigabits per second LPDDR4. Feature counts include over 3 million LUTs, on-chip memory of close to 1 gigabit, and 104 PAM4 SerDes. In summary, Versal Premium brings high-speed networking IP to the Versal family. It comes with a hardened SoC shell that is up and running at boot. Hardened NOC enables easy swapping of kernels in programmable logic. 4th generation SSIT enables large devices economically. The resulting architecture is an adaptable SoC with very large bandwidth and compute density. Thank you for your attention.
Thank you, Martin, Yohan, and Matt for a great talk. We have time for a few questions. The Slack channels have been active again, and I saw Matt answering some questions already. Appreciate that, Matt. The first question comes from Manoj Shiroge. He would like you to comment about the latency through the NOC access points. So how much time does a soft PL kernel or hard IP take to get on and off the NOC?
So who takes it? I can. You can, Matt?
Okay, sure. So the NOC is very much user programmable. So users can provide QoS and latency requirements on the NOC, and the latency that is experienced in a NOC transaction is very much user dependent based on those settings, and not only the configurations in the user design, but where the interfaces in the device are located. There's documentation on the NOC and tools available today to evaluate specific scenarios in simulation or in design.
Okay, thank you, Matt. A related question comes from Nathan Yakimic. He would like to know what kind of constraints you have to place on PL kernels so that they can be moved around the device without needing to be recompiled.
Yeah, I'll take that one. So to move them around within a specific device, they will have to be placed in programmable logic patterns on the chip that are repeated. And I don't think at this point there's good documentation on that yet. To do the same between different devices, there's a similar constraint. Only certain subsets of devices in our families, not only premium, share repeatable patterns of fabric. And again, I don't think as of now there's good documentation on that.
Okay, thank you, Martin. Related questions by Nathan Brookwood and Ian Cuttress. Can you comment on total die area, and also does the 92 billion transistors apply to a single die, or is it for the grouping for the total number of die to combined?
Yeah, I'll take that. Total die area we cannot comment on. Sorry. The 92 billion transistors applies to our largest stacked silicon device, which has multiple SLRs.
Great. Thank you, Martin. Questions about the memory interfaces. Tao Jiang would like to know if LPDDR4 and DDR4 can be enabled both at the same time.
Not sure about the question. They can be enabled at the same time in
so
different
can I simultaneously
DDR blocks.
Can I run simultaneously LPDDR4 and DDR4 interfaces?
In two different DDR blocks, yes.
Okay, thank you, Martin. Yeah. There was a question on support for LPDDR5.
We cannot comment on that at this point. Please keep an eye on future announcements.
Okay, and then there was a question also on memory bandwidth. What is the maximum bandwidth of HBM on Versal? The question asked by Hamid Reza Zuhuri.
Same answer as the last question. I cannot comment on HBM at this point. Keep an eye on future announcements.
Nathan Yakimic has another question related to AI engines. Are there plans to branch AI engines into DSP-focused functions versus AI-focused functions? And are there plans to support half precision and other degenerate integer data types?
Did you want to take that one, Matt? Or?
Well, I think that falls in the bucket of a roadmap question. We're not at this time in a position to share on roadmap, obviously.
Another question by Hamid Reza Zahouri. Can you comment on the automatic partitioning of user design between AI, DSP engines, and programmable logic? So are there any tools that aid a designer with partitioning across AI engines and programmable logic?
So we launched Vitis tool stack last fall to target software developers to help with that very problem. We'll continue to have Vivado as an entry point for our hardware developers. Vitis is an effort to address developers at the software level, and you'll see more of that in the future from Xilinx.
Great, thank you, Matt. Question by Anand Iyer. Can external chiplets attach to the Xilinx NOC?
In theory, yes. I don't think there are external chiplets today that could.
Okay, thank you, Martin. And let's take one final question. By David Cantor. Have you looked at using the interposer for long-range routing connections using larger wires with lower resistance? Or does the TSV latency defeat the purpose?
So we already do that. I'm not sure how long range means in this question, in this particular question, but the signaling that we run in interposer wires are very long wires.
Okay, great. Martin, Yohan, and Matt, thank you for your time. I know you've been active in the Slack channels. A great talk, and hopefully you can stick around and answer some more questions. Thank you.
Thanks.
Now I would like to introduce the third talk in the session. The session is called FPGAs and Reconfigurable Architectures. We're switching to a very different kind of an architecture. This next talk is by Tenstorrent, introducing more details on the coarse grain logic chip they've built. The talk is actually entitled Compute Substrate for Software 2.0 and heavily focuses on explaining how the architecture works and software support for the device. Presenters are Ljubisa Bajic and Jasmina Vasilijevic. Ljubisa is the CEO of Tenstorrent, a company he co-founded in 2016 to develop and bring to market a new computer architecture aimed at addressing the growing demand on data-centric computation. Ljubisa holds an electrical engineering degree from the University of Toronto. He's worked at many different companies, including ATI, AMD, and NVIDIA. Jasmina Vasilijevic is Director of Software at Tenstorrent. She received her PhD in computer engineering also from the University of Toronto. She spent time working at Intel PSG /Altera, leading an ML compiler team targeting FPGAs. And then she spent the last 3 years leading the compiler team at Tenstorrent. So I'd like to introduce Ljubisa and Jasmina and their talk.
Thank you very much for the introduction, Ralph. Although the title of our presentation says Compute Substrate for Software 2.0, what it's really about is the age-old story of the hare and the tortoise, in which the sporting rabbit lets the tortoise run ahead for a couple of decades in order to catch up with it very quickly in about a year when he decides to. This, in a nutshell, is a summary of our situation with machine learning compute demand and Moore's law, which has been governing the ability of the semiconductor and the hardware world to provide compute capacity to machine learning. So the two key curves to focus on here are the orange one and the blue one at the bottom. And what you can see is that there's this very rapidly growing gap between the two. I tried to overlay a couple more just for thought experiment purposes. So let's say optical or analog and nanowires works out, we get a one-time speed boost of about 1,000x. That's what's shown on that purple line. The two dashed lines are showing Moore's law as it pertains to clusters. So in one case multiplied by 10,000, so this is kind of reasonable cluster sizes today. In another case, it's multiplied by 100,000, which is larger clusters, which we're trying to enable and probably others are going to bring forth in the coming years. Either way, you can see that the compute demand for machine learning is skyrocketing. It's just a matter of time when the two curves intersect. And in other words, when the rabbit catches up with the tortoise. So the two ways that we've chosen to try to work on this problem is, for one, enabling huge scale-outs, so bigger ones that have been attempted before, so enabling machines that put us into the 100,000 node territory. For the other is dynamic execution, and the idea here is that we would like to embrace every way of intelligently dropping work and foregoing computation and machine learning, akin to what our brains do, in order to take the current slope of the machine learning compute demand curve and bring it down to something much more compatible with Moore's law. So a couple of slides about scale-out. So large clusters are already normal. Pretty much all modern models are being trained on them. Some of the biggest ones are even being inferenced on them. At this point, we had to transition from a shared memory programming paradigm to a private memory programming paradigm, as every node in these clusters has a private memory space. Usually they have a bunch of GPUs. Data movement between the nodes needs to be explicitly controlled and planned. For a while, this was made a bit simpler by embracing the data parallel view of training for models. That era is kind of over. Models are too big to fit on a single node now, so model parallelism is the norm that's being deployed today, and with it, one is exposed to the full complexity of cluster-level programming. So hardware and software-wise, we wanted to enable the largest clusters ever. And from the hardware side of things, what this meant was tightly integrating networking and compute on a chip, enabling computation to be scheduled directly at the level of packets, exposing packet routing control to our graph compiler. All of these together are aiming to let us build clusters with hundreds of thousands of nodes in them and expose all of this huge machinery as a single device in PyTorch so that machine learning practitioners don't need to worry about parallelization, communication, all these items that are below their preferred level of abstraction. They can focus on developing their models. From the software side, what this means is a move from shared memory programming paradigms in which each processing unit can see the entire memory space, and when one needs an array element or a tensor element, they can just issue a load and get it. When one core sees a tensor manipulation, say a transpose or an unsqueeze, a lot of these just come down to different offsets and striding in the same memory buffers that are visible to all of them. Where the primary compiler challenges were creating a parallelized schedule of the workload and then loop nest optimization. We move into a world in which chunks of data are owned by particular nodes. There's only local visibility of data. Any communication needs to be planned and implemented explicitly. Tensor manipulations, so like that same transpose, become not only manipulations, so not only local transposes, but in the general case, also required scheduling of data movement between nodes to implement, as shown in the diagram here. In this kind of world, the hardest challenges are with data transfer, communication, consuming tensor manipulations without having to stall the machines and stop doing math. We try to solve these problems holistically by retrofitting our hardware with a variety of features that try to help, and then splitting them effectively between our runtime software layer and our compiler. A little bit about dynamic execution. So what all is dynamic execution? It's enabling control flow at runtime so that a machine learning model practitioner can say, well, if the power in this tensor is above a certain threshold, compute the remainder of the neural net this way. If it's below, compute it another way. This is actually currently missing, and it enables the level of control to machine learning practitioners that should, by a good degree of slope reduction to that machine learning compute demand curve. Fully embracing sparse compute And in particular, I'm referring to dynamic sparsity here, so sparsity in activations, sparsity in weights during training. Fully embracing dynamic precision, so that at model control or at heuristic control, we can choose fine-grained what data type to use for what computations. And finally, taking compression for all it's worth. Machine learning presents a lot of compressible data. This needs to be embraced fully and used as far as it can be. To give the next level of idea of what this means, I make an example of a matrix multiplication that can be done in order n complexity. So beginning with the left, we start with a standard matrix multiplication, which most of us here know is, when implemented naively, it's an n-cubed operation. We move to the middle, where we assume that the model has intelligence within it to determine which blocks of the output matrix need to be computed for a given example, and which don't. If the hardware and underlying software stack support making use of this, it enables a linear speedup. So you hit 50% sparsity, you speed up 2x theoretically. You hit 90%, you speed up 10x. So this is pretty nice, but it's far from starting to close the gap. However, the rightmost example actually makes a fairly serious dent in the problem. Here we show an example where chained operations produce sparse results. So one of the operands is sparse, the result is also sparse. If the underlying hardware and software support it, this offers theoretically 4x speed boost even with just 50% sparsity. With 90% sparsity, we crossed the 100x mark. The important thing to notice here is that regardless of the numbers shown here, the real significant factor is that this meaningfully reduces the slope of the machine learning demand curve and brings it into something like compatibility with Moore's law. A little more on this topic. It's generally applicable, works for training and inference. It also works for models that aspire to generality, like GPT-3, so models that try to do a lot of things without a specialization. Pruning, which is currently somewhat popular, fails at both and only works for models that are relatively specialized. Certainly doesn't work for training. Now, as I mentioned before, this approach requires models that can dynamically choose subsets of blocks to compute during each pass. There's a number of ways that machine learning folks have figured out to attack this problem with. Mixture of experts from Google, locality-sensitive hashing-based approaches to determining the important outputs, pre-pass-based approaches where you do a simplified pre-pass and use that as a map of what to compute. More close to our territory, this requires hardware that can really fully utilize this kind of model structure and deliver that speed up that I was advertising on the previous slide. So we strive to make our hardware such. And with that, I hand it off to my colleague Jasmina, who's going to give you a lot of details about both our hardware and software architecture and how we implemented the details of it to attack both scale-out and dynamic computation.
Thanks for the introduction, Ljubisa. I will take you guys for a deep dive through our architecture and software, and I'll describe them interchangeably in order to give you a good sense of our holistic solution. Here we go. So I'll start off with a high-level view of Grayskull. Grayskull is the name of our first production chip, and it's also the first incarnation of the architecture that I'll present today. It's a cluster on a chip, so it's composed of 120 compute cores. Now, each core has its own unique instruction queue, and it progresses independently at its own pace, while occasionally communicating with the other cores in the grid. The cores are connected via a 2D bidirectional torus NOC. The NOC was architected in-house, and it's highly optimized for machine learning workloads. In terms of connectivity, the PCIe block connects to host, and DRAM is also accessible from every core of the device. Now, zooming into a single core view, as Ljubisa mentioned, everything that happens on our system happens in the format of packets. Packets get computed, and packets get moved around the NOC and the memories. The packet processor is a 3 teraop vector SIMD engine. It's powerful, but very, very flexible and programmable. It can actually execute C code-based kernels, and we've mapped a large number of PyTorch math layers onto it. It contains DSPs with a multitude of various data formats, but but most importantly, it actually natively handles sparse compute to achieve speedup. Next, the packet manager, it's in charge of executing all data transfers between compute, memory, and between the cores as well. And it completely deburdens the compute engine from all of the data movement complexity. Each core also contains 1 megabyte of local SRAM, and as mentioned, has access to DRAM as well. Finally, there are 5 RISC processors on every core, small but powerful single-issue processors. They execute our runtime software. So, continuing on with the challenges that Ljubisa introduced earlier, we need to parallelize every compute layer across the cores of the device. So to do that, we split the tensors amongst the SRAM blocks on each core. And we also need to move the tensors between the cores during runtime. So sometimes we're moving the tensors between the different compute layers, but sometimes the tensors need to be moved around during the compute itself. In addition, the application graph that we get from a machine learning framework, it doesn't just contain compute instructions. Most often, there are various kinds of tensor manipulation instructions between the compute as well. And these TMs, they don't change any of the values inside the tensor, but they reshuffle the data within the tensor. So to actually correctly connect the compute nodes, all of the data reshuffling has to happen during runtime. And all of this has to be executed while achieving high performance, meaning we have to overlap compute and data transfers. We have to efficiently use the NOC. We have to efficiently use the memory bandwidth when we read and write to memory. So combining all the goals together leads to a compound complexity, which we attack with our full stack approach and a tightly coupled software-hardware co-design. So three main architectural components are here. First, the AOT graph compiler, which parallelizes compute and packetizes all the tensors. Next, in hardware, the movement of packets is facilitated by the packet manager block. And finally, in runtime software, the runtime software works together tightly with the packet manager to dynamically allocate memory space in SRAM on every core, but in off-chip memory as well. And I'm going to describe these three architectural components next. So first, the graph compiler. It takes each tensor, it splits it into multiple mini tensors, and for each mini tensor, it generates header information, which essentially then just becomes a packet. Now, each packet is assigned the packet ID, which is stored in the header, and everything that happens further during compilation as well as during runtime is done in terms of these packets and their IDs. So there are no pointers and there's no pointer manipulation. Now, there are many different ways to packetize a single tensor, and some packetization strategies are more desired than others. First, to utilize the NOC bandwidth well, the compiler has to choose the right packet size, and packets can be heterogeneous in size even for a single tensor. And second, we have to execute all the TM instructions during runtime. So technically, the TMs can be executed via complicated read-write memory patterns. It's easy to create the patterns themselves, but this can easily kill performance during runtime. So what the compiler does is it performs an optimization where it assigns some TMs to be performed in line midstream by the packet manager, while other TMs are expressed as memory access patterns. So it actually generates a combination of these two approaches in order to maintain performance. Next, the packet manager. So to understand, the easiest way to understand what the packet manager does is by looking at what packet compute does. So the packet compute engine is powerful, very programmable, but it has only a very local view of what is happening in the system. It simply gets input packets to be computed from the packet manager, and once it computes them, it sends output packets back to the packet manager, and that's it. It's actually the packet manager that has a global view of what is happening across the entire chip. So it has access to NOC, it has access to local SRAM and to remote DRAM, and it also has insight into what is happening on all the other cores in the system. So it's able to perform all the required multi-core synchronization, all the required data movement, data storage, and TMs as well. And the way that it does that is via the 3 building blocks that it contains. So at the very, very bottom, the router moves packets across the NOC, and in some ways it's a textbook router. So it takes care of back pressure, it guarantees ordering, it guarantees deadlock-free execution, but it's also highly optimized for machine learning workloads, and it has a very flexible and very efficient multicast and gather operations. In the middle, the data transfer engine, it's tightly coupled with the router, but it operates on a slightly higher level of abstraction. It's actually aware of the application that it's executing, so it receives an entire instruction queue from the compiler, and the instruction queue tells the data transfer engine how and when to take care of all the required multi-core synchronization and handshaking. Like data ready signals, memory space ready signals, and so on. It's actually aware of the state the other cores are in, and it uses this information to, for example, decide when to start sending data to remote cores or when to allocate space in its local SRAM in order to receive data from remote cores. So finally, the tensor manipulation engine at the very top, it contributes to performance in 2 ways. So first, it performs the complex memory access patterns assigned by the compiler, but second, it has a tiny bit of storage within it. So within this storage, it can actually load a single packet and reshuffle it in place. And this way, the compiler can program the TM engine to perform tons of tensor manipulations efficiently inline midstream as it's reading or writing to the memory. So finally, the runtime software. So the packet manager works in tight collaboration with the runtime software, primarily in order to achieve dynamic memory allocation. So all buffers are allocated and deallocated during runtime, and the runtime can actually control the storage target as well. So this allows us to store buffers in SRAM if they can fit, but also gives us the flexibility to overflow to DRAM or even to host memory space if necessary. And second, the runtime software enables control flow and control flow graphs to run on our hardware. So the RISC cores can actually execute any type of conditional instruction within the graph, so if statements, for loops, while loops, and the resulting control flow decisions are reflected by jumping around in the instruction queues that both packet compute and packet manager are executing. So finally, a brief look at our flexible scheduling and parallelization. So obviously there is a desire to support very flexible parallelization, and the reason for that is because any single parallelization approach eventually plateaus as you increase the number of cores across which you parallelize. And the way to maximize performance is to stack up as many parallelization approaches as possible. So on our architecture, models can be pipelined, and actually each pipeline stage can execute multiple compute layers in sequence before progressing to the next pipeline stage. In terms of model parallelism, we can do the simple case where each layer is parallelized across the entire chip if that's possible, but also layers can execute across any number of cores of the chip and run in parallel if the graph contains parallel opportunities. So tying it all together, our full stack approach has unlocked a number of desired targets. First, we achieve high performance by enabling a tremendous amount of concurrency. So not only does every core progress independently at its own pace, but the building blocks within the core, so the packet manager and the packet compute, they operate in parallel too. And as a result, compute and data transfers are fully overlapped. Second, on a system with tons of asynchronous concurrent behavior like this one, the ahead-of-time graph compiler has no chance at accurately predicting buffer lifetimes or managing memory well. So we leave this task to the runtime software. Now, the compiler generates storage-related hints, but the actual memory addresses of each buffer are determined at runtime. And third, most importantly, we have fully unlocked dynamic execution. So we've enabled runtime compression, and we achieve speed up from the increased amount of data locality the compression brings. And again, the runtime dynamic memory management ensures that. The packet compute engine can natively handle sparsity, through which we achieve speed up as well. And finally, the RISC cores can execute performance penalty-free control flow on the device right at the edge of the compute. So that's all for me. This concludes our deep dive, and back to you, Ljubisa.
Thank you, Jasmina. Jasmina and I have spent some time talking about high-level architecture, about the macro-level situation facing machine learning and computer architects. I'd like to conclude this presentation by talking a little bit about Tenstorrent as a company, about our products, about our status, and plans for the future. Tenstorrent was founded 4 years ago to develop a ground-up computer architecture for the new age of data-centric computing. Since then, we have grown from the 3 founders to around 70 employees across Toronto and Austin. Our team has deep expertise in CPU, GPU, and FPGA-based approaches to parallel computing. Over those 4 years, we have worked on 3 chips: Drawbridge, which was a small 14-nanometer test chip; Grayskull, the part that Jasmina talked about, which is currently in evaluation with multiple large customers. Grayskull will be transitioning to production in late fall this year. And Wormhole, the first part that fully realizes our vision of converged networking and compute. Wormhole includes an integrated network switch, 16 ports of 100 gig Ethernet, 6 channels of GDDR6, and a compute fabric similar to Grayskull. We expect to have Wormhole in-house by the end of the year. It forms the basis of our plans to enable larger compute clusters than anyone has been able to build before. This slide shows the progression of BERT performance numbers with various aspects of dynamic execution enabled. The first number, which leads the industry on performance per watt, is with no conditional execution enabled and 16-bit floating point numbers for apples-to-apples comparison to GPUs. The second assumes a very light subset of conditional execution enabled. And finally, the last assumes modifying BERT to include sparse operations as described earlier. It's still a work in progress number, here to show the promise of our approach primarily. We've spent an equal amount of time on our software stack over the years. We architected our software to aim for full compiler generality from the get-go. The list of machine learning models below shows a subset of workloads that we're using to test our compiler generality. You can see representatives from all major neural net categories in the list. Our software is under evaluation by customers currently, and we will open up the beta version of it for public access in our development cloud on November 1st this year. While we spent a lot of time on functionality of software, we also had strong goals in the areas of usability. In order to make our product maximally approachable to the ML community, we implemented complete integration with PyTorch. Through TorchScript, PyTorch's preferred deployment flow, Onyx, as well as a native device. Regardless of how many processors are used in an instance, a machine learning practitioner sees them all appear as a single device in PyTorch, avoiding the need for them to worry about parallelization, communication, all these difficult aspects of cluster-level programming. Finally, we will be shipping an automated deployment flow, allow existing models that have been trained on GPUs to automatically gain benefits from our conditional compute features and approach. So in summary, we're going to slow the hair down, speed the tortoise up via conditionals and scale. And we're going to do it in a way that is maximally easy to adopt and use by the machine learning community. I hope you all enjoyed our presentation, and thank you very much for listening.
Thank you, Ljubisa and Jasmina. Great talk. Very good overview of your architecture and also great explanation on how your software toolchain maps networks to the architecture. Many questions in the Slack channels, and I also see Ljubisa in particular, you've been answering questions. I really appreciate that. I've picked out a few to ask to the larger audience. Starting with some chip and architecture related questions. Can you comment on why you have chosen to integrate 5 RISC cores. Why not 4? Why not 8? What's special about the number 5?
So there's a couple of different answers to that question. One is that usually in the sort of mindset where you run multiple threads of code and with the aim of them competing for a hardware resource and keeping it fully utilized, the driving metric that drives the number of threads that you want to have concurrently running is your latency to memory, because the most often occurring reason for stalls and for one of them failing to utilize the, in our case, compute resource or the packet processor, is that there's an outstanding load. So our latency to the local SRAM, the megabyte of local SRAM, is 5 clocks. So that's the kind of 5 magic number reason. The other one is that empirically, as we ran architectural simulations and later on Verilog simulations, we found that it works well with that number, so that we are able to keep the utilization high.
Ljubisa, thank you. A question about the NOC. It seems many devices have NOCs. What makes your NOC special? And in particular, how is it tuned for AI?
Again, I'll touch on a couple of things, although it's by no means an exhaustive list. One is that we built in more comprehensive support for efficient multicasting than you generally see in designs that are targeted at other applications. So we have specific features that target very efficient multicasting in rectilinear regions. We have other features that target efficient multicasting in completely unstructured sets of cores. The other set of reasoning is that we put in a lot of hardware offload, which allows sort of semi-static configurations of data flows through the network, which persist for a chunk of the workload and then automatically move on to another sort of set of configurations to support the next computation that's scheduled by the compiler. So I'd single out those two as the most important.
Okay, great, thank you. And a follow-up question, so from Manoj, he would like to know if you can comment on the frequency and the width of the NOC.
Yeah, absolutely. So I mean, our design as of now is a single clock domain design. So all the compute and the NOCs, they all run at the same clock frequency. As we know, frequency depends a lot on voltage, and the frequency voltage pair determine power. So we're capable of running our parts from at up to 1.5 gigahertz as things stand. We're not going to be productizing Grayskull, at least not in the first incarnation at 1.5 gigahertz. We're productizing it in the form factor of a 75-watt PCI card, which is going to be running somewhat lower than that number, but that's as good as I can tell you right now. We're still essentially running characterization and trying to determine the VF points we're going to be shipping at. And even when that is done, it's going to be a per part VF.
That's great. And can you comment about the bus width of the NOC?
I can. I'm kind of taking it out from memory here, but we actually have two 2D toruses running in opposite directions, and I should have mentioned this before. The reason for that is that way we can guarantee locality and communication between kind of locally collaborating groups of cores. So between those two NOCs, we have four sets of 64-byte interfaces on every core. I think that's correct. I'm hoping I'm not off by a factor or two somewhere there.
That's great.
And when you combine that with the clock frequency, you can tell what the bandwidth is.
That's great. Thank you. Great answer. Question about data type support. There's a question says you support FP32. Do you also support TF32?
So that's a chip-specific answer here. So in Grayskull, we have B floats and halves. For multiplication, we do not have TF32. For basically for the array mode, high throughput math mode. We do have TF32 in SIMD mode. So if you want to run something like, a series expansion, you can do it in TF32 on Grayskull. For Wormhole, which is our upcoming part, TF32 is supported in array mode as well.
That's great, thank you. Also, another question on the differences between Grayskull and Wormhole. Why the choice of LPDRAM on Grayskull versus Wormhole moving to GDDR interfaces?
So Grayskull, while it can do training, was optimized to be an inference part. So the bandwidth offered by LPDDR4 was sufficient for all of our targeted workloads. Wormhole, again, while it can be a decent inference part, it's optimized to be a training part, and it wanted some more bandwidth. Now we chose to provide that bump in bandwidth via GDDR6 primarily because of the extreme cost of HBM that it levies per die.
That's great, thank you. Another related question, can you comment about the dimensions of the tensor core unit, or how wide is the SIMD if it's a SIMD unit?
Yes, I can. So the in SIMD mode, it's 64 wide. And so it's kind of similar to what you would see on a, on a typical GPU, and it behaves in a very similar way when programmed. Now, as far as the array mode goes, it's a little bit more difficult to summarize. And if you don't mind, I'll actually double check on the side and I'll respond in Slack.
That's great.
In terms of number of multipliers in this case.
That's great, yeah. So switching to some questions on the tool chain. Perhaps I'll inject a question myself. So how general purpose is your architecture? You talked a lot about machine learning examples. Can your architecture support other workloads as well? And is it just a question of what you tune your software for, but is the architecture broader than machine learning?
So the architecture can definitely support things other than machine learning. It was designed to be really a general purpose computer architecture, which solves the problems that are inherent to going to a many core private memory approach. The primary sort of hard link to machine learning is the data type choices, where in order to get good performance per watt and performance per silicon area, we did have to sort of focus in on the data types that are at this point more popular for machine learning than they are for other applications. We also had to completely forego some other data types, which would be nice to have for a general computer like doubles, for example.
Very good, yeah. Dan Wilkinson would like to know if your compiler supports only static graphs or if dynamic graphs are supported as well.
Dynamic graphs are definitely supported. In fact, if there was a single overriding reason for us to exist as a company, it's that we wanted to enable sort of highly dynamic, fine-grained conditional execution at runtime, and thus a part of that goal necessitated that our software stack can consume and do well with dynamic graphs and control flow graphs as part of the larger workload description.
That's great.
I'll just briefly add to that. So the control flow graph is supported through the compiler and all the way down to the hardware, and the packet manager and the compute, they adjust to the control flow decisions.
Great. And then a high-level question from Ping Ping. If you could compare your architecture to GraphCore's IPU, what would be the main differences?
It's a bit of a difficult question to answer, given that our understanding of the GraphCore architecture is fairly superficial. But I mean, the first thing that pops into my mind is that while they also try to solve the many core private memory problem, right, both at the hardware and at a programming level, the approach they took, which is this bulk synchronous parallel programming paradigm in which they essentially explicitly split the work into computation and communication phases is, fairly diametrically opposite of what we try to do. So we tried very hard to enable high utilization and complete overlap of communication with compute, whereas from the get-go, their choice has been to just separate the two and kind of live with the fact that there's chunks of time where you're not computing. So to me, that seems like most likely the largest obvious thing that I would call out. But again, take with a grain of salt. We're not experts on their architecture.
Good. Thank you. Appreciate you attempting to answer that question. So perhaps just time for two more questions, and that is one you may not be able to answer. What is the die size, or if you could provide an approximate die size, Vidya Vajgopal would like to know.
Yeah, absolutely. We do not mind. It's 620 millimeters squared in 12 nanometer global foundries for Grayskull. For Wormhole, I actually don't have the exact number, but it's in the same ballpark.
That's great. Perhaps we'll end it over here. We are running a little short of time. There's many more questions in the channels. So if you don't mind answering a few more, you've done a great job so far. Thank you, Ljubisa and Jasmina. A very interesting talk, and there's a lot of interest. Thank you for your time.
Thank you very much, Ralph.